we're going to learn oscillatory motion in this chapter. Oscillation is repeating and periodic motion about a point of stable equilibrium. We learned stable and unstable equilibrium. For stable equilibrium, if we give some force or disturbance, some perturbation to that object in stable equilibrium, that object tends to go back to the equilibrium position. That's the definition of stable equilibrium. So if you give some small force, for example, here, the spring gives some force, right? Restoring force. So if you give some disturbance or force to an object in stable equilibrium, that object will undergo repeating and periodic motion about that equilibrium position. There are lots of oscillatory motion in nature. For example, there are mechanical, we just saw mechanical oscillator, right? Pendulum and so on. And also there are electrical oscillator, electromechanical, optical, biological, even in human body there are oscillations. For example, voice production is related to the oscillation of this ear part in the neck, and also there are oscillations in economy and social properties. Climate also shows us in astrophysics, chemical. There are many phenomena in nature that can be described by this oscillatory motion. How can we describe this oscillation in physics? You need some parameters. Parameter called period. Period is a time for a complete cycle of the oscillation. How long it takes between, for the object to undergo a complete one cycle of oscillation. That time is period. And 1 over period is called frequency. Frequency is, by definition, how many times the object goes through, how many cycles the object goes through per unit time. And the unit is 1 over second, which is hertz. And angular frequency, I will explain later why we use angular frequency, but it is defined as 2 pi times frequency, and the unit is radian hertz. And actually we need 3 parameters. So another parameter we need is amplitude. Amplitude is the maximum peak position of the oscillation. Here, this is maximum displacement. And there is one more parameter that describes this. We need to describe oscillatory motion, which is phase. Phase is basically the starting point, describes starting point. For example, compare these two oscillations described by this displacement function xt. These two have the same amplitude and same angular frequency, so same period, right? But here, this term is different, right? Here is 0, here is phi. This is what we call phase. Depending on this number plus something, omega t plus something, and then that something determines the initial starting point here. When this phi is 0, starting point is here. When t equals 0, it's maximum. Cosine function is maximum. So the displacement is 0. So depending on the phase, this quantity here, starting point changes. And the simplest form of oscillatory motion is simple harmonic motion. Okay, simple harmonic motion is a motion of an object when the force or torque, the restoring force or restoring torque, is linearly proportional to the displacement. When we find the centripetal acceleration, for example, if an object moves in circular path at a constant angular velocity omega, then to describe the motion of this the uniform circular motion, we decompose this vector in x component and y component, right? X component is r cosine theta. Theta is omega t, and y component is r sine omega t. So each component of this circular motion, x component and y component, x component is this projection, right? Projection here. X component is here, cosine omega t, r cosine omega t. Y component of the circular motion, r sine omega t. Both of these components of uniform circular motion is basically simple harmonic motion. We use the simplest form of oscillation, which ignored any additional other than the restoring force, we ignore any other forces, for example, frictional force and so on. Here, now, what happens if we include damping? Damping some frictional force. So, for example, so energy is here's a damper. Here, this is what we consider so far. Mechanical energy conserved. So amplitude does not decrease as a function of time. But if we have some friction between the object and the wall, or air due to the air, or some other frictional force, then that dissipates mechanical energy, right? Mechanical energy no longer is conserved. What if we consider one more force on top of this spring force, restoring force, and then damping force? If we give some driving force, driving force. So driving means additional force than the spring force. You give some additional up and down the external force with some different frequency than the spring, the omega naught of the spring. So driving frequency of the driving force can be different from this angular frequency, which we call natural frequency, different from the natural frequency of the spring itself. Okay. For example, when you ride a swing, okay, 그네 swing, then you can go back and forth so then it's a pendulum. It's a pendulum. Go back and forth by itself. But someone can push you. Someone can push you to increase the amplitude. That's driving force, for example. So now the equation of motion is very complicated. On top of this restoring force and the frictional force, we have additional driving force. Driving force, here we just consider sinusoidal driving force. That's the most, the easiest and simplest driving case. So driving force is F naught sine omega dt. Here omega d doesn't have to be the same as the natural frequency omega naught, which is determined by mass and the mass of the object, oscillating object, and the spring constant. Mathematics course, some differential equation course, but I will give you the answer after a long time. Eventually it's a special solution basically. So if you plug into this equation, you will find that A here actually is a function of omega. We can plot this amplitude as a function of driving force frequency like this. So here x-axis is driving frequency, driving force frequency. You can change with giving driving force very fast with very fast frequency or very slow frequency. Then at some point it's not just increase with driving frequency or decrease with monotonically changes, but it shows some peak, okay, at some position, at some driving frequency. That what we call this kind of peak happens in any physical phenomena. If this kind of peak happens with some parameter, we call this resonance. So resonance occurs with the driving frequency. When C is 0, that means so damping force is 0, damping is 0, but driving force, we give some driving force, then you can see this one is 0, C is 0, C is 0. Then when is this amplitude is maximum? When is the resonance occur? Resonance occur when omega driving frequency is equal to the natural frequency of the system. So maximum occurs near the natural frequency of the system. This is very obvious. Again, think about the swing, okay, with swing motion. When you ride a swing or your brother ride a swing, you want to increase the amplitude. You want to make him go higher and higher. How many times do you have to give force? Once per cycle. That means you have to give force every time every time your brother undergoes a complete cycle, which is natural frequency of the system. Your driving force should give with the same frequency as the natural frequency to give the maximum effects, to increase the, if you push when he moves down, then it'll decrease the amplitude. You have to give the force when he goes up and then goes back. and then starts moving, then you have to give the force. So you have to give the force with the same frequency of the natural frequency of the system to generate this resonance. That's very obvious if you imagine. But when this damping is non-zero, this is not exactly equal to omega 0, omega naught. It changes, right? Deviates as damping increases. It's a little bit gets smaller than the natural frequency. And you can see damping is gets smaller. The resonance peak increase. Even when damping is 0, it's infinite resonance. So this sharpness of resonance is measured by Q factor. We define this Q factor. How much energy is lost per cycle depends on how sharp this resonance is. So when damping is small, then it's sharp. Resonance becomes very sharp, right? So for low, KAIST is lower, then the system lose less energy, okay, per cycle, then resonance becomes very sharp. Q factor is high. So Q factor is related to the damping coefficient, and also how much energy is lost per cycle. Energy is less lost, or damping is less, then resonance becomes sharp and Q factor becomes high. Here's the answer actually. Resonance frequency is dependent on this KAIST. When KAIST damping is 0, it was omega naught. Here's the end of the chapter 13. We learned oscillatory motion in chapter 13. The most important part is simple harmonic motion we learned. And so when we included damping, it's a little bit more complicated, right? Because the force is not now included. Force includes non-conservative force. Amplitude decreases as a function of time. And also resonance occurs when we include some driving force with some frequency. As a function of frequency, the resultant amplitude of the system changes, right? And shows some peak at some position. Thank you.